All right, hey everybody, welcome back to 10600. So today we're going to talk about how to choose the best model, how to make all of the choices in regression that we've been talking about over the past few lectures. So let's get started. All right, so we've discussed, it might seem like about 1 billion different choices that you can make when you're choosing a regression model. So you can choose what data to collect and how to measure each example. You can clean up the data in a bunch of ways by, for example, removing outliers, or if you weren't able to measure every feature of every example, you might have to fill in missing features, or there might be a wide range of more complicated processing. For example, it's fairly common to try and detrend data if you believe that the examples you're getting are changing their mean over time, or to filter data to try and improve how close to IID it is. You can also decide what feature transforms to use. So for example, you can toss out some of your input features, or you can include interaction terms, or you can include nonlinear functions of these variables. You can choose the ordinary squared loss or a robust one like absolute or Huber loss. You can choose regularization, the most common being ridge regression. And if you have regularization, you have to choose how strong it is, or the relative strength of the prior and the data. And you can choose whether or how to use automatic feature selection like forward stage-wise. So that's a lot of choices. And unfortunately, in addition to being difficult to think about all of these choices, there's another problem that leads to, which is called overfitting. You've probably heard overfitting a lot, but it's a catch-all term for all of the problems that result from fitting too complicated a model to using too little data. And you may have seen this graph before. It's a fairly common cartoon, fairly accurate cartoon of what happens in overfitting. So the way this graph works is that we have error on the y-axis, meaning, for example, mean squared error. And on the x-axis, we have some measure of model complexity. So we could have, for example, the ridge parameter lambda could be big, or it could be small. And small ridge parameter means light regularization, means a more complicated model. And by a more complicated model, I mean one that is more sensitive to the exact training data that you happen to receive. So complexity is sort of the opposite of stability. Now, if you look at your error on your training set, right, it's going to go like this as you increase complexity, because by definition, when you increase complexity, you're better able to fit your training data. So here, lambda big is actually pulling you away from your training data. Lambda small is letting you fit it closer. So this is going to be on the training set. But if you take this model that you fit and you evaluate its error, for example, its mean squared error, on new data, which I'll call the test set, you're going to get very different behavior. For a while, it will track the training error pretty well, maybe be a little bit larger, and then it'll start to drift away from the training error, and eventually it can actually go up. And so over here is what we'll call underfitting. You're using too simple a model. And over here is what we'll call overfitting. You're using a complicated model, but it's so complicated that your test error has started to move away from your training error. And obviously what we'd like is to, be just right, the sort of Goldilocks zone of here where maybe the test has started to move away from the train a little bit, but it's still going down, and we want to sort of catch it at the bottom. And of course, it's really hard to do that, right? If we could do that perfectly every time, then we wouldn't need a course to talk about it. But this is sort of where we're aiming for. And there's a lot of different ways that you can make a complex model. You can have too many parameters to learn or not enough regularization, for example. But the most important thing, and the thing which people maybe don't realize until they take a machine learning course, is that model complexity includes every choice that you've made while designing the model, right? So if you started off fitting a decision tree and then you decided not to fit a decision tree but to go to k-nearest neighbor instead, that choice of moving from a decision tree to k-nearest neighbor, that actually increases your model complexity compared to if you had just started with nearest neighbor to begin with. Right? So it's the entire history of how you arrived at the model that can lead to overfitting. And that sounds almost magical, right? Like why would a model overfit more depending on how you arrived there? And the answer and the cause of overfitting in general is what's called selection bias. So here's selection bias. This maybe the best thing to do is to look at a picture. So let's say we're evaluating a lot of models to decide which one to use, right? So for example, in regression, we evaluate infinitely many models and choose the one with the smallest mean squared error. Now, I can't draw infinitely many models on the slide, so what I'm going to do is just say that we're evaluating 4 different models, 1, 2, 3, and 4. So this is the model number. And we're going to evaluate their error. And lower is better for error. So we're going to be using something like mean squared error here. And there's going to be some true mean squared error for each one of the models that we're looking at, right? So I'll draw it like this. You know, the dash represents the true mean squared error. And by true, I mean that if we took an independent sample that was incredibly large and measured the mean squared error of our model on that new sample, this dash is the level that we'd get. And so since we don't have an infinitely large sample, the actual measured error of each of the models is going to be a little bit different from this value. So maybe it's here for model 1, here for model 2, here for model 3, and here for model 4, right? And so the true best model, the one with the lowest error, is 3, right? But it looks like model 4 happened to get lucky, right? Its error, as estimated on our training set, was a little bit lower than the error for model 3. And so we'll actually choose model 4, right? So this is true best, the true best model, but we pick this one. And so this is a problem. This is overfitting. We picked the wrong model because of the difference between its true error and its observed error on our training data. And this, it's kind of a subtle effect, right? Like our error is unbiased, right? It's equally often higher or lower than our true error. So it seems a little strange that even with an unbiased error estimate, we're going to be led to pick the wrong model. And the reason for that is that if you have a whole bunch of unbiased estimates, but you take the best of them, that best one is biased, right? Because, you know, the chance that, let's say, all of them are biased to be slightly worse than they really are, except for one that's exactly right, that chance is really low. Much more likely that a few will be better and a few will be worse, and then you're more likely to pick the one that's better. So that explains selection bias. So selection bias explains the existence of overfitting. The next question is, why do you get the U-shaped curve? And the answer is because selection bias gets worse and worse as you get more and more models to choose from, right? So if we had models, you know, 5 and 6 and so forth, right? Then, you know, maybe model 5 is also not the best, but it happens to get a slightly larger error, right? And actually, let's even draw it, let's draw it this way, where model 5 is a little worse than model 4, but it has a little bigger positive error estimate. And maybe model 6 is almost as good as model 3, but it still has a slightly bad error estimate, right? And so now instead of picking 4, we'll pick 5, right? And the distance between the cross and the dash is even larger, right, than it was for 4. So this here is the amount of selection bias or overfitting. And the more models we have, the larger a chance we have to get bad selection bias. I just realized that I did not open up the ability to see what the TAs are telling me, so I'm opening it up right now. I apologize if people have been asking questions that I didn't know, and I'll try and answer them soon. All right, so that's selection bias, and that's why you get a U-shaped curve. And selection bias increases as model complexity increases. And it also gets worse as our training data set gets smaller because the distance between the dashes and the crosses gets larger. And it also gets worse as we make more and more discrete choices. So if we're choosing between, let's say, decision trees and deep neural networks, right? And if we look at our data to make that decision, there's a little bit of selection bias that comes from that choice, right? We selected the one that looks better on our data, and so that means that we have a possibility of being fooled because one of them got lucky. And so I've been talking about more or fewer when really most of the time we're choosing among infinitely many models. And for that case, you can think about discretizing our model space, right? So if we have a linear regression model with 5 parameters, we have a 5-dimensional grid, or if we have 8 parameters, we have an 8-dimensional grid. And if you think about it, an 8-dimensional grid of a given resolution is going to be larger than a 5-dimensional grid of that same resolution. And so having more dimensions is more or less the same as having more models to choose from, right? It's a little bit more nuanced than that, but that's a pretty good first approximation. If you've seen covering numbers, that's maybe the way to formalize that intuition. All right, so overfitting happens and it's bad, and so we would like to detect and eventually fix overfitting. And the simplest way to detect overfitting is holdout data, also called validation data. And so what does that mean? That means that we take our available data, our training set, and we split it into 2 parts. The first part, we call that our training set. So instead of using the whole thing as our training set, we just take a part of it and use it as our training set. And the remainder we reserve, and we call it the holdout or the validation set, to estimate, we reserve it to estimate the true error of the model that we fit on the training data. And because we're not optimizing the parameters of the model on the holdout data, there's no selection bias there. We get an unbiased estimate of the error of our model, and so that is good, right? We're reporting an unbiased estimate of our model's error instead of an optimistic one that we get by optimizing. So, all right, problem solved, right? Maybe not. So there's 2 problems. The first one is if we keep too much of our data as holdout, we hurt our performance, right? We would like to train on as much data as possible because the more training data we have, the more accurately we can fit our model parameters. And second, we don't just want to detect overfitting, and instead we want to fix it, right? So we might want to, for example, if we're using ridge regression, we might want to tune the ridge parameter lambda by optimizing mean squared error on the holdout set. And that's a good idea in general, but as soon as you start to make choices, as soon as you decide whether to use decision trees or deep neural networks, or as soon as you pick a value of your ridge parameter by looking at the holdout set, selection bias starts to creep in again. And so we're sort of in a catch-22, right? We want a lot of holdout data, but in order to be able to get good tuning of things like ridge parameters without too much overfitting, but we want a large training set in order to be able to tune our model, our regression weights without overfitting. So this is kind of bad, right? So I've seen over and over again people fool themselves by taking too much of a peek at the holdout data, right? So it's really easy to be tempted by that huge pile of beautiful data sitting over there in a locked safe, right? Or you should keep your holdout data in a locked safe. And it's really tempting to go over and look at that data to make just one little decision, one more little decision. The problem is every time you look at your holdout data, you're incurring selection bias. And so in practice, what you should do is think about this decision you're making. How important is it? How much is it likely to increase the performance on the training set, to reduce training error? And if the answer is a lot, then it might be worth looking at your holdout data, because you'll increase selection bias and therefore overfitting a little bit by looking at your holdout data, but you'll improve your training error by a lot, and so that will more than counteract that effect. And if the answer is only a little, if you're making some little tweak to try and get the last few percentage points out of your training data, it's better not to do it. Just don't look at your holdout data and make the tweak as best as you can without looking. And you will be happier because you won't have lost more in selection bias than you gain by optimizing on the training set. And I can say this, and I say this every time I teach a machine learning class, but inevitably people are still tempted. And so I just want to offer one more warning, which is that I've seen a lot of machine learning competitions and I've run a few of them. And typically the people who win them are people who only look at their holdout data a very small number of times. Meaning, you can count them on the fingers of one hand. So we really are in a catch-22, right? Our data has to be either in our holdout set locked away or in our training set, at which point we can use it for training, but we can't figure out how to tune our, we can't use it to tune our ridge parameter, for example. So are we stuck? Thankfully, no. There's this cool trick that you've probably heard of called cross-validation. And what cross-validation does is it lets us use all or almost all of our data, both in the training set and in the validation set. And that sounds, miraculous and impossible, but it turns out to be pretty straightforward, and the cost is basically just computation time. So the way we do it is we divide our data into k disjoint pieces, and these pieces are called folds, and we treat each fold in turn as the validation set. So that means that there are k-1 other folds. We make them our training set. And then we test, meaning measure our error, let's say mean squared error, on the validation fold. And then we repeat. We do this for every possible choice of one of the k folds as the validation set. And we average all of the resulting validation losses. And that means that our final error estimate is made by averaging one loss for every training example. We've managed to use our entire training set for validation. And every time we train, we're using k-1 of the folds. So we have a fraction k-1 over k So for example, if k is 10, we get 90% of our data to use for training at any given time. So that's pretty cool. Now, the problem, like I mentioned, is computation time. We've trained k models instead of just one, which is, at least naively, k times more expensive. But computers just keep getting faster and faster, so that's less and less of a problem. Although people also keep thinking of more and more expensive ways to train machine learning models, so it becomes more and more of a problem. And the other thing is that using a cloud service, right, we can fire up k copies of our training script, and we can do all of these things in parallel, right? So we can trade money for time if we want to. We can, pay Amazon EC2 a lot of money and fire up k copies and have it done in just the same time as one training run. Or we can fire up k over 2 and pay half as much money and take twice as much time. So I have an animation here about overfitting. About cross-validation. And let me just bring it up and show it to you. So here is, let's actually go a little bit farther back. So this is just going to be an animation about validation rather than cross-validation. So here is our training set. This is a classification problem, so all of our y's are either 0 or 1. All right, we have audio trouble again. I wonder why the last 2 lectures have been worse for audio trouble. Hopefully, like before, if I just wait, it'll get better, so we'll see. All right, so here's our training set. So all of our y's are 0 and 1, and the x's are the horizontal and vertical axes on the page. And what we can do is we can pick a random subset of our data to be the holdout set. We remove it, and we fit a machine learning algorithm on the remainder. So if we do regression and split at where the regression line passes through a half, we get a decision boundary between the 2 classes. That's actually a pretty reasonable classifier. And then we can add back in the holdout group, and we can compute the error. And you can see this guy is, here we're computing classification error. We could perfectly well use mean squared error if we wanted to. So here's a classification non-error, a correct point. It's on the 0 side. Here's a classification non-error. We got this one right because it's on the 1 side. But here is an error because there's a 1 that appeared on the 0 side of the decision boundary. All right. So then we get an estimated error rate, in this case, of 1/3 because, well, that's 1 out of 3 wrong examples. So that's validation. Here's cross-validation. So here I've taken my training examples and I've split them into blue, red, and green, 4 points in each one of the folds. So this is going to be 3-fold cross-validation with 4 examples in each fold. And we can remove the green group and fit on the rest, and we get, there's the decision boundary we get. And then we add back in the green group, and we check how many are errors. right? And then we can remove the red group and fit on the rest and add back in the red group and check how many of those are errors. So we got 1 error on the green, 2 on the red, and if we do it on the blue, remove blue, fit, add back in, we get 2 errors, right? So we got, out of 12 data points, we got 5 errors, right? And so 5/12 is a 42% error rate, which is not great, but this was just a small example. All right, so I'm hearing that our audio is very unstable. I'm going to try stopping and restarting the stream. I apologize for that. Let's try, I'm just going to stop the stream and restart it again and see if that helps. So everybody will have to re-look at the YouTube page probably. All right, so I am back. I've restarted the stream. Can people tell me, can the TAs please tell me which, whether there's a part of the lecture that I need to go back over again, or whether I should just keep going? All right, so that was cross-validation. Good, okay. So the new stream appears to be good. I'm getting the feedback. If anybody has questions, just please let the TAs know what areas of the lecture I should try and repeat. And until I hear something, I'm going to go on in the lecture notes. All right, so we've done cross-validation, and that we had k-folds, which means we have k different sets of parameters. We got one parameter set, excuse me, every time we trained on a different set of k-1 folds. We're going over the cross-validation. Oh, okay, so I'll go, I'm hearing that the error was pretty, the audio error was pretty bad for cross-validation. So let's go over this plot again. So here is my training data, and I've split it into 3 different groups, which I've colored blue, red, and green. And the 3 different groups are the 3 different folds. Oh, people are requesting I go over the entire overfitting slide section again. Okay. Wow, so starting back from 2. Okay. All right, so we'll go over again starting from 2. Apologize about the audio troubles. Hopefully they're better now. All right, so overfitting is what happens when we try to fit too complicated a model on too little data. And there's this this cartoon of what typically happens when we do this. So there's a bunch of different measures of model complexity. In general, a complex model is one that's really sensitive to the exact training data that we get, and a simple model is one that is not as sensitive. It's stable with respect to the training set. And so for example, one measure of complexity would be how strong a ridge term we add in ridge regression. If we have a strong ridge term, that means we have a simple model because we're fairly stable. And if we have a large ridge term, we have a simple model, and if we have a small ridge term, then the model is less stable, and it goes, it responds very strongly to the training data. Let's see. So I'm being told that I wasn't supposed to go all the way back to section 2, but more back to section 5, detecting overfitting. Okay, so let's skip back up. That's great. That was sad to have missed, 90% of the lecture. So let's go back to detecting overfitting. So we know that it's a possibility. We know that it results from selection bias. And so we would like to detect it and then hopefully fix it. So to do that, what we need is, well, one of the ways to do it is to have what's called a validation set or a holdout set. What that means is we split our available training data into 2 parts. So let's go back on the animation to here. And so here's our training data. And what I mean by splitting is that we just pick some fraction of our data, the blue points here, call that the holdout group, and just remove it, right? Then once we've removed it, we optimize our model parameters on the remaining data. So here we've got, this is a classification problem, so y is either 0 or 1, and we can fit a regression model to this data, and we can split at where the regression prediction passes through a half, and that will be a good decision boundary. That's a pretty decent classifier. And that looks like this, right? So here we've got, we've split our decision boundary so that the circles are more on this side and the crosses are more on that side. Now once we've done that, we can add back in the holdout group like that, and we can compute our error on the holdout group. And here we've got 1 error out of 3 holdout points. And so we will say that our estimated error rate is 1/3, because that is the, well, 1 out of 3 is 1/3. I guess that's not surprising. All right, so there's a couple of problems with holdout data. There's, the first one is if we have too large a holdout set, then we've taken a lot of data out of our training set, and that's a problem because we can't then use that to optimize our parameters. And the other is that we don't just want to detect overfitting, but we want to fix it. For example, we might want to tune our ridge parameter lambda to optimize our mean squared error on the holdout set. And to do that, for example, we might just try a grid of different possible values of lambda and pick the one that has the lowest holdout error. But as soon as we do that, as soon as we start to try and make choices based on the holdout set, we incur selection bias on the holdout set. And so we're sort of losing the point of having had a holdout set in the first place. And that's really kind of an important point. I won't say as much this time as I did while the audio was apparently going out, but really it can be a problem it can be a big temptation to peek at the holdout data and make just one more little decision, and that will actually reduce your overall performance on a fresh test set. Because what can happen is that the benefit you get on training set can be outweighed by the increase in selection bias that you get by making another decision based on the test set, or the holdout set. And so because of this, it's actually common to split our available data into 3 or even more pieces. If there are 3 pieces, we can call them the training set, the validation set, and the test set. And the distinction is that we optimize our model parameters on the training set. We make model structure decisions, like whether to include a ridge term and how strong to make the penalty. We make those decisions based on the validation set. And then finally, And only once or only a handful of times we use the test set to get an accurate estimate of our model's true performance. All right, so that's validation. Now let's look at cross-validation again. So here's cross-validation. So in cross-validation, we split our data into several pieces. Here, 3 pieces, blue, red, and green. And we hold them out one at a time, right? So if we hold out the green points and make a fit, here's what we get. And then we put the green points back in, and it looks like we made a mistake on one of them, right? And then if we hold out the red group, here's the fit we get. The regression parameters point this way, and then the decision boundary is normal to the regression parameters. And so when we add back in the red group, here we've made 2 errors. And then when we remove the blue group and fit and add back in the blue group, we make 2 errors as well. And so we made 1 plus 2 plus 2 is 5 total errors. And so we estimate a 5 out of 12 or 42% error rate. All right. So that's called cross-validation because we use every fold to check every other fold. And then we switch and use the first fold, use the second fold to check the first fold. So cross-validation is great because it gives us a larger training set. We get to use k-1 over k of our data. So if k is 10, we get to use 90% of the data as training data. And then we get to use all of our data for validation because our final error estimate combines error estimates from all of the folds, meaning that every training example participates in validation. Computation time could be a problem because we're training k models instead of 1, but sometimes there are tricks that let us share effort, and at a minimum, what we can do is we can fire up k instances on Amazon EC2 and get all of our k training runs to finish in the same time as just 1, because it's embarrassingly parallel to run the folds. And so what that means is that instead of splitting into train, validation, and test data, we just combine our train and validation data. And often people will call that a development set or a dev set. And we'd use cross-validation within the dev set to both optimize our model parameters and optimize our model structure. And then we rarely check the error on the test set. So one problem with cross-validation is that it leads to k different sets of parameters, one for every fold. So we'll say wj for fold j. And which one do we report? So maybe the simplest strategy is to try and pick the best parameters. So you could test each one of these on a little bit of extra data that you held out from the cross-validation and just report the best one. And that's okay, but it requires us to hold out some data that we couldn't use in our cross-validation. And so that's not good. Another strategy, and maybe the most common one, is to re-optimize. Re-optimizing means that after we've decided on the model structure, meaning, let's say, what variables to include, what transformations, how strong a ridge penalty, all of those decisions, we go back and take the entire development set, use it as a training set to fit the model parameters for our final model structure, and we report those final model parameters. But what I would call the best strategy is not to choose, right? The only way to win is not to play the game. We report all of our parameters that we fit on every single fold. And so we get what's called an ensemble of models, which just is a fancy name for a list of a whole bunch of models. And we can use this ensemble to predict by making a prediction with each model and then averaging together those predictions. And that's called model averaging. And in linear regression, the prediction of model J is Wj times x on example x, and if we average that, that's 1 over k times the sum of all of the Wj x's. And if we just put the parentheses in a different place, right, that means that we could have gotten away with just reporting the average value of the model parameters. But that's not what I mean by model averaging. Model averaging means you make a prediction separately with each one of your models and you average the predictions. And in the case of linear regression, you can save yourself some computation time by just reporting the average parameters. And the reason that's important is that we can use model averaging on other machine learning methods besides just regression. And in that case, the difference actually makes a difference. The other interesting thing is that we can skip averaging our predictions together, and we can report the entire list of predictions. And that list is kind of, it has more information in it than just the mean, and so it's kind of nice to have that extra information. In particular, we can think of the list as representing how uncertain we are about our prediction. If all of our models in our ensemble make the same prediction, then we're confident, and if their predictions vary all over the map, then we're not very confident in our prediction. And we can go even farther than that, and we can use, let's say, kernel density estimation to fit a distribution for what we think y is given x. So that's going to be an estimate of the conditional distribution of y given x based on the models that we fit. And that's called a predictive distribution, that conditional distribution p of y given x, and all of our information that we had before, like the decision of what model class to use and the list of model parameters. That's called the predictive distribution. And so that's a nice way to summarize the output of an ensemble. The other nice thing about an ensemble is that it lets us go beyond just reporting prediction error. So up to this section, we've been talking mostly about accurately estimating and reporting our prediction error, but there's a ton of other questions we could ask. For example, we might want to ask whether some regression weight, Wij, is non-zero, which is to say whether one of our inputs is useful for predicting one of our outputs. Or we could ask whether one of our inputs tends to be associated with increases or decreases in outputs, which is to say we want to know whether Wij is positive or negative. Now, the ensemble lets us answer this sort of question. For example, if Wij is positive in most of the models in our ensemble, then we'll say, yes, we think Wij is probably positive. And what do I mean, by the way, by saying that Wij really is positive in some, abstract sense? Well, you could go as far as to say that, there's actually, you've made a causal model of your data, and that's the true causal mechanism has a positive influence from xj to yi. That's not where I want to go. You'd have to make a lot more assumptions in order to do that. But what I would like to say, what I do mean by truly positive, is that if you generated a much larger training set and trained your model on that, you would find that Wij is positive in that much more accurate version of your model. And again, this is an example of being careful about what you say about causation, right? Because the regression by itself only determines correlation. And in order to go from correlation to causation, you need to either make assumptions or intervene in the world by doing a randomized controlled trial. All right, so maybe even more interesting, we can take our model ensemble and interpret it as a sample of size k from our posterior distribution over W, right? So from probability of W given all of our data. And so if we want to answer a question about W, we can ask how often that the answer would be yes for the models in our ensemble, and report back that fraction as an estimate of the probability. So, if Wij is positive in 9 out of 15 models in our ensemble, then we say that P of Wij bigger than 0 is 9 over 15. Now, for the case of cross-validation, people do this, but it's only sort of informal and heuristic. We're actually going to see a little bit later an example of a method called the bootstrap, where there's a little bit more of a theory to justify making this interpretation. But before we go there, I want to talk more about the sorts of questions we can answer using a model ensemble. So far we've been talking about questions that have binary answers, like, is Wij positive, right? Now, we might want to know what is the exact value of Wij, or if we want to keep the question to yes or no, we could ask, is it 0 or not? And that can be a little bit trickier to get a satisfying answer, because based on the assumptions of a regression, right? Like if you justify your regression by saying that W was selected from a Gaussian distribution, and then the data were selected from a conditional linear Gaussian model based on W, then, well, the answer is clearly no. W cannot possibly be 0. It was a sample from a normal distribution, and there's no chance of exactly hitting 0 when you sample from a continuous density. Now, that may be true, at least given our assumptions, but it's not satisfying, because that answer doesn't depend on the data we observed. There was no point in having built a model, collected data, fit the model, right? There was no point in having done any of that if you're just going to say, no, it can't possibly be 0. So we have to change our modeling somehow. The simplest way to change our modeling is to assign a strictly positive prior probability of Wij being 0. Right? And if we do that, then the posterior probability can also be non-zero, and in fact it can be anywhere between 0 and 1. And that might seem to answer our question, except that there's no really impartial way to set the prior probability of Wij equals 0. And in particular, it can very strongly influence what our posterior probability is if we select a different prior probability. So we still need to look a little bit farther, right? Like, it's not going to be convincing for us to argue to anybody that W is 0 or non-zero based on posterior distribution from an arbitrarily chosen prior. There are lots and lots of approaches to get around this, but one that I'm going to talk about specifically for this class is what's called a credible set. So you may have heard of a confidence set or a confidence interval. Credible sets are the Bayesian version of those. What is a credible set? An alpha credible set is a set that a set in our parameter space that covers a fraction 1 minus alpha of our posterior probability over parameters. Right? So for example, if in our posterior distribution 95% probability W is between 3.72 and 4.05, then that interval, 3.72 to 4.05, is a credible set. And the 0.05 or the 0.95, right, those tell us what's called the size or the level of our set. So in particular, the size alpha is the probability of the set not covering the true value of the parameter. And so we can use credible sets to answer the question of whether Wij is 0 or not. We'll say that we have evidence that it's non-zero if the credible set doesn't contain 0. And if the credible set does contain 0, we'll say we don't have evidence. And the strength of the evidence depends on alpha. If we have a very small value of alpha, meaning the credible set covers a lot of posterior mass, then we have strong evidence. And if we have a large value of alpha, meaning a value close to 0.5, the set doesn't cover much of our posterior, then that's weak evidence. And there are a lot of different ways to pick a credible set, but maybe the simplest is what's called the symmetric credible set, where you or the symmetric credible interval, where you just, for a 1D parameter, you pick your set so that there's an equal probability of going below or above it. All right. So that is cross-validation, model averaging, and credible sets. And just to connect back to what you guys have been doing, in the programming part of the homework 1, which is due this coming Monday, you have to make a whole bunch of decisions, right? So you have to decide what variables to include or not. You have to decide what interaction terms to include, how to transform your data. And so as you do that, you would like to make those decisions accurately. And so that means that you can use a strategy like cross-validation or like bootstrapping, which we'll talk about in a second, to help you make those decisions. Same thing with, for example, choosing a ridge parameter. We can try to choose the value of the ridge parameter by looking at cross-validation or bootstrap error estimates, and we'll get a better value there than just picking one out of the air or looking at one that gives you low error on the training data. Right? And so this is a you will hopefully get a chance to use these methods very soon, because your homework is asking you to answer questions of the exact sort that these methods are designed to answer. All right, so let's move now to talking about the bootstrap. And the point of the bootstrap is to get around a couple of limitations that cross-validation has. The first is what I talked about before, that cross-validation only gives you a heuristic approximation to the posterior distribution over parameters. The second is maybe a smaller problem, but it can be a problem nonetheless, which is that there's a limit of n folds if we have n training examples. We can't split our folds smaller than one training example per fold. Now, you might think that you'd never want to go beyond that number of folds, but in fact, sometimes you do if you want an accurate estimate of the posterior probability of some event, like whether, like if you want to, for example, get very accurate estimates of where the ends of your credible interval are, then you might want more than n folds. So to reduce or fix both of these problems, we'll switch to the bootstrap. And in the bootstrap, just like in cross-validation, we're going to repeatedly split our dev set into a training set and a validation set. But the way we split is different. In each iteration of the bootstrap, we're going to resample a training set of size n. And the way we're going to do that is we're going to pick a random training example out of our training set and put it into our bootstrap set, which is called a bag. So we're going to sample one of our n training examples just by generating a uniform random integer between 1 and n, and we put that example into our bag. And we just do that over and over again. And we don't worry about whether we select the same example twice, and so typically we'll select some examples twice, some maybe even 3 or 4 times. And we just do that until we have a bag, which is the same size as our original training set. And everything in the bag are called the in-bag samples, surprisingly enough. And everything that's not in the bag are called the out-of-bag samples. And we're not going to prove it, but it turns out that on average, a fraction of just under 40% of our examples will be out-of-bag. And those are going to become our validation set. And then bootstrapping is just like cross-validation. We train on the in-bag examples, and then we measure our loss on the out-of-bag examples, and we do that over and over again until we have enough iterates, enough estimates of our error. And unlike cross-validation, we can repeat almost as often as we want because there's a very large number of possible bags that we could sample, and so we're probably not going to run out of bags. But just like in cross-validation, we report at the end the ensemble of one model per bag. And this is called bootstrap aggregation or bagging. And historically, I think the term bootstrap aggregation came first, and then it was shortened to bagging, and then that led to each one of our training sets being called a bag. I'm not sure of that, but that's my understanding of the history. So here's an example of the bootstrap. So here's a continuous distribution, and we're going to make a very simple model of this distribution. We just want to estimate its mean. And so we sample some points, it happened to be 272 of them, from this distribution, and we get, this is a histogram of the points we sample, and if we estimate the mean from that sample, we get about 1.6. And so that's our point estimate, right? We just get a single estimate of mu, and we'll call that mu hat. But that doesn't tell us anything about how confident we are. It doesn't tell us anything about the posterior besides its mean. So to approximate the posterior, we're going to run the bootstrap, meaning for b times, we're going to resample 272 points by just drawing with replacement from this distribution. And so, here are 3 of the bags we get, and we get different means in each one of the bags, right? And so the variability of those means helps us understand how confident we are in our original estimate mu hat, right? And just to be clear, taking the mean of one of the bags corresponds to refitting our model in the jth iteration of the bootstrap. And so we get a model parameter, which is just a mean mu hat, for each one of our bags. And we can use our bootstrap sample to answer questions like what's the probability that mu is bigger than 1.6, or what is the standard deviation of our estimate mu hat. And so I actually ran this with 100,000 bags and got an estimated standard error for mu hat of 0.0818. And it turns out that this is a simple enough example that I can compute the exact standard error of mu hat, and it's 0.0825, right? So that differs by less than 0.001, which is pretty good, although it did require a lot of bootstrap iterations. Now, it turns out that if you want a really accurate estimate, you need a fairly large number of replicates, but a much smaller number of replicates can get you a coarse estimate of your certainty. And in particular, if you do it in this example, you're off by only about 0.1, which is not so bad. All right. So I mentioned that Bootstrap has some theory behind it. And that theory is basically that it's possible to prove under appropriate assumptions, which are actually fairly strong, that every iteration of the Bootstrap gives you another sample from the posterior distribution, at least a fairly accurate approximate sample. And like I said, the assumptions can be kind of restrictive, but they're reasonable in some sense, and you can sort of see why they're reasonable. So the first assumption is that you need a large enough original sample, because if you have a small sample, you're not going to see sort of the true variability of the data, and every one of your bags is going to contain a lot of exact repetitions, right? So you're going to have sort of a poor representation of your true probability distribution. The second assumption is that your model class needs to be, they call it smooth. And what do we mean by smooth? Informally, it's basically that the model should be stable. It shouldn't react strongly if you grab one of your training examples and wiggle it a little bit. And so the more sensitive your model is to wiggling a training example, the higher the sample size you need before the bootstrap starts to become a good approximation. So, all right. It looks like we're losing our sound again. We're almost at the end, and so instead of restarting the stream, basically I think it's probably best if people who couldn't hear just look at section 12. And in particular, there's basically 3 things that we need to make sure of in order to get the bootstrap to work. Large enough original sample, smooth enough model class, and it's actually important that the sample be IID as well. So I think for 2 reasons I'm going to stop here. Reason 1 is the bad sound, but reason 2 is that today I actually can't hold office hours right after class, so or rather I can't hold office hours past about 3. So I'm going to stop now and hold a short office hours, and anybody who can who still has questions, please ask them on Piazza. So we'll stop now, and office hours start now and go until a little bit before 3.